Hello, everyone, and thank you for joining us today. My name is Kartik Choudhary, and my partner name is Jen Sorte. We are pre-final year students from Indian Institute of Technology, Jodhpur, and today we will present the paper "Count Me In: The Adaptive Crowd Estimation with Wi-Fi in Smart Cities." We have selected this paper as a presentation for the Mobile and Pervasive Computing course. This paper was presented in IEEE in 2022 by Gurkan Solmaz, Pankaj Baranwal, and Flavio Cirillo. So here is the overview of what we will be discussing today and the key points we will cover. First, we will start with the background of the study and providing some context and explaining the motivation behind our research. Next, we will move on to the problem statement, which will outline the specific research question that we aim to answer and the gap in the literature that we wanted to address. After that, we will present our framework, which outlines the theoretical underpinnings of our research and the conceptual model that we use to guide our analysis. Then we will discuss our methodology, which will explain the research methods we use to collect and analyze the data. This will include details about our sample data, collection instruments, and data analysis procedures. Next, we will present the results of our pilot study and edge device. This will include the details about the preliminary testing we conducted to ensure that our data collection methods were sound and that our edge device was working correctly. After that, we will move on to the experimental evaluation, outlining the results of our main study. Then we will move on to the discussion and limitation. This will involve detailed analysis and interpretation of our results, including the consideration of strengths and weaknesses of our study and any limitation that we encountered. Finally, we will conclude our presentation with a summary of our key findings and their implication of theory and practice, as well as some suggestions for future research in this area. So that's our agenda for this presentation. We hope you will find it informative and engaging, and we look forward to your questions and feedback at the end of presentation in the comment section below. So coming to the background of the study, the main motivation behind doing the crowd estimation was rapid urbanization. So nowadays, it has resulted in cities accommodating a large number of people, which has made crowd estimation necessary. Also, efficient city services such as crowd management, tourism and retail, evacuation modeling, and epidemics monitoring require accurate crowd estimation. So, this is the main motivation behind our research. The main problem statement that we are going to address through this paper is addressing the crowd estimation more accurately than existing approaches, and yes, importantly, adapting to the dynamic changes. So, what is the problem with existing Wi Fi based systems? Why do we need another approach? Well, the existing systems don't provide highly accurate crowd estimation. Also, they do not adapt to the dynamic changes in the wild, such as unexpected crowd gatherings. The existing approaches for crowd estimation in urban areas include conducting surveys at busy subway platforms and asking passengers about the density of people during their journey and then manually verifying. Also, there are existing computer vision based technologies solutions, but they all are privacy invasive and energy hungry. So, all these existing approaches suffer from the accuracy due to lack of adaptation to the dynamic changes in the city. So, to address all these limitations, we will be presenting the Count Me in this presentation. The framework of counting quite simple. It mainly applies the ML for calibrating the Wi-Fi scanners. The actual data, which is approximately the correct count estimation. In this paper, we will be terming it as a near truth value, and which is collected from the people counting cameras placed. Additionally, there are also Wi-Fi scanners placed for the crowd estimation. You can see in the figure. The raw data is collected from the Wi-Fi scanners as Wi-Fi probe packets, and during the training period, the system learns the correlation between noisy Wi-Fi probe packets with RSSI, which is the received signal strength indicator, and people counting cameras based on temporal features such as day of week and hour of the day. Now you can see in the crowd estimation period, the CountMeIn leverages only Wi-Fi measurements and calibrates them using the trained machine learning model. So the application of machine learning here enables removing the advanced people counting sensors after the training period for the crowd estimation and which helps to minimize the privacy invasion, deployment cost, and energy consumption. So, coming to the methodology of the CountMeIn, CountMeIn is a system that uses Wi-Fi probe packets to estimate crowd size. The system is calibrated using the counts from stereoscopic cameras, which are considered to be the near ground truth in this case paper. So this calibration process can be completed quickly without using the people counting sensors again. You can see in this figure, it shows the functional view of the two main processing, the training period, where the relationship between the Wi-Fi probe packets and the near ground truth is determined using the raw data collection from Wi-Fi and camera in parallel, and the use of the calibration system to predict crowd size using the trained machine learning model. The Wi-Fi probe packet accounts are noisy, so an off-shelf device, which is the people counting camera with built-in image processing and people counting module, is used to provide the calibration interface. So here the architecture mainly comprises of four steps, which is the data pre-processing, RSSI, and bucket filtering, training feature selection, and finally using the two ML methods, polynomial regression and neural network. Here in the database preprocessing, the Wi-Fi calibration steps involve processing data collected from two couch DAB databases, storing raw Wi-Fi probe packet details and camera data. The databases which are separated, they are separated due to different transmission intervals because the two data which are collected from the Wi-Fi probe packet details and camera data, they are not in the same intervals. So that's the reason why we have separated into two databases. Uh, uh, Again, a process is run over the raw databases to generate a new database for suitable time series calculations, which is necessary for the preprocessing. And the aggregated data includes unique devices detected by the Wi-Fi scanners and the number of people counted by the stereoscopic cameras. And then it is recorded in a new database with details of each 1 minute interval. Further proceeding, we come to the RSSI and bucket filtering. So the RSSI values particularly range from -100 decibel to 0 decibel and indicate the strength of the received Wi-Fi packet. The more closer the value is around 0 decibel, the stronger is the signal strength, which is the RSSI value. Records with an RSSI value below -87 decibel are filtered due to are filtered to reduce noise. We have already filtered the value below -87 decibels to reduce the noise. Bucket filtering is used to remove the static devices, which are printers or other things from the environment which continuously broadcast Wi-Fi probe packets but should not be included when predicting people count. So buckets of observation are created based on the maximum observation count for a given time period, and devices with observations greater than the bucket maxima are considered as static devices. You can see in both of the figures that we observe in our initial measurements that choosing an appropriate RSSI threshold beyond the probe packets are considered as too far off, which helps in reducing some noise from the Wi-Fi probe packet count data while still preserving the overall pattern over time, which you can see in the figure. Coming on to the training feature and selection. After completing the data pre-processing steps to format data on a per minute basis and reducing the noise from the Wi-Fi data, we then begin to start with the optimization problem and the equation of which you can see in the figure, where t is the time period, y of t is the calibrated people count, function of x denotes the calibration function, and xt represent the raw Wi-Fi probe packet count. Here YT represent near ground truth value detected from the camera, and E is the error value, and N is the number of time periods. So in the figure, you can see the daily pattern of people's movement in the area can be observed, and using temporal features such as hour of the day and day of the week, it can help detect crowd size pattern throughout the day while accommodating variation due to weekends and weekly events. The exact timestamp of the data point, it is not included to avoid overfitting the model, So that's the reason we have divided into 1 minute of interval. And this problem is modified to include the temporal features. So here we discuss the two main machine learning approaches which we have incorporated in our CountMeIn model, which is the polynomial regression and neural network for the crowd estimation optimization problems. The dataset is divided into training, validation, and testing sets. We have used the Reg and Lasso's regression for training polynomial regression models. And for the neural network, we have used the ReLU activation function, a customized RMSE loss function, Adam optimizer, and SGD with Nesterov momentum for the optimization function. The performance metrics used is a mean absolute error, and the neural network architecture has 3,196 trainable parameters. So here, this article emphasizes the importance of choosing the right regression model to ensure a good performance and generalization. You can see the input feature of raw probe packet count shows multicollinearity with the other two features, hour of the day and day of the week. Therefore, we have chosen the ridge regression and lasso regression for training as they provide least squares estimate that is less biased to multicollinearity.
Hello everyone, I am Jayant and I'd like to take over from here and continue the presentation. Pilot study and edge devices. A pilot study was conducted in Gold Coast, Australia. The objective was to use the field data to determine if CountMeIn is feasible in big open spaces in a smart city. Two Wi-Fi scanners and two stereoscopic cameras are part of the testing equipment. Two locations were covered, firstly a pedestrian street and secondly an area near the beach. The camera sensors were removed from the module once enough training data was collected, and then CountMeIn was started for the crowd estimating phase. Additionally, a CountMeIn lab device was created as an all-in-one deployment module in the lab environment. The device operates the whole pipeline of CountMeIn system from the sensors to the phase of training for a crowd size estimate. A Raspberry board is linked to four fisheye cameras which were coupled to a mobile power supply. While not being utilized during the pilot research, this gadget is used to access the scalability. We will now discuss various evaluation methods which collectively work best for the model. It includes various type of evaluation metrics, comparison with other state-of-the-art methods in the same domain, RSSI filtering and development of neural networks, and data features and types of training procedures that were run on the model. Now let's talk about evaluation metrics. For this, we take into account a variety of statistical metrics for the evaluation based on strengths and biases, since doing so increases the likelihood that we will get the correct estimate of how well the models perform in various circumstances. The first one on the list is MAD, that is mean absolute deviation. MAD is an absolute value, making it resistant to outliers. The larger the MAD, the more significant variability in the data exists, hence the data is more spread out. Next we have MAPE, that is mean absolute percentage error. This metric gives a percentage error that is easier to take into account than other numerical metrics. Next we have WAPE, that is weighted MAPE. In the previous metric, if the data has zero values, then calculation of MAPE means dividing by zero, which is a problem. To overcome this issue of handling zero valued points and to avoid the asymmetry of MAPE, we make use of WAPE. Lastly, we have root mean squared error, that is RMSE. Since at moments the data may contain high errors which are less in numbers, to tackle this problem we take into account the RMSE. State-of-the-art methods. The paper has compared CountMeIn with two other state-of-the-art methods, namely crowd estimator and PFA, that is pedestrian flow analyzer. Crowd estimator is a model that approximates crowd sizes with multimodal data for IoT services. And PFA is a statistical analysis of the actual number of pedestrians for Wi-Fi package-based pedestrian flow sensing. Carrying the topic from the previous slide, in this slide, we have a figure which compares the error performance of various aforementioned state-of-the-art methods with CountMeIn. It shows the performance of models over different weeks of the testing period. We have used two metrics here, namely RMSE, root mean square error, which is red bars in the graph, and MAD, mean absolute deviation, which is shown by the blue bars. The A graph sets the baseline for two error metrics used, which were calculated for a raw Wi-Fi PP count. Graph B and C shows the same thing when calculated using crowd estimator and PFA respectively. Graph D shows the performance for CountMeIn model. We can clearly see that crowd estimator exceeds the baseline values because the ground truth is not actively available for correlation. PFA, however, performs well, but CountMeIn has almost half the RMSE and MAD error values than PFA. We can further bring down this error rate by using the early means of errors. RSSI filtering and neural networks. RSSI filtering is widely used in this space to improve the performance and reliability of wireless communication. In the next few slides, we will evaluate the results of ridge and lasso regression over the filtered data and compare various neural networks. In this figure, we see that the models have been trained for several 2-week periods and the accuracy has been calculated for a 5-month data. The figure shows MAD values and the degrees of polynomial coefficients, after which the trained regression model began to overfit. Both lasso and ridge regression performed equally well for most of the training data. However, lasso regression outperformed the ridge regression in some areas where the training data had several anomalous data entries. The difference in the output can be due to the fact that the loss function of lasso contains the regularization terms in absolute form, which can help set unnecessary features to zero, unlike ridge regression. In this figure, we can see performance of various neural network models. The data for this comparison is averaged hourly for both training and testing. We compare the neural networks on the four previously mentioned evaluation metrics. It can be clearly observed that the neural network with the Adam optimizer and RMSE loss function achieves the best performance on all metrics. In addition, the bigger model slightly outperforms the smaller model when the same optimizer and loss functions are used. Data features and training time. We always try to minimize the errors. In order to do so, we try various features like time, PP count, and other training data features. In the next slide, we will discuss in brief about this metric with the help of some other figures. On the top left, we have a figure that estimates error using MAD, RMSE, and MAPE. The error is generated by the regression models using different sets of feature vectors. This set will include two features specifically. Firstly, time, and secondly, Wi-Fi PP count. It is observed that the model trained using both features performs considerably better than the model trained on timestamp or Wi-Fi PP count. On the other hand, we see that the timestamp model performs better than the Wi-Fi PP count model. This happens because the PP count data is a bit noisy, and in reality, the people count follows a periodic pattern which helps the timestamp model to perform better. On the right hand, we have another figure which helps us to figure out the length of the training data. It compares the error generated by taking into account models with the different lengths of training data. We see that 1 week of training data is not accurate as we know that a particular week in the year can generate more crowd than any other normal week. On the other hand, a flatter curve of average accuracy over test data is produced by training for 2 or more weeks. For the algorithm to understand time-based pattern as well as noisier patterns present in Wi-Fi PP count, utilizing 2 weeks data appears optimal. At the last, in the bottom, we have a table that shows minute and hourly crowd estimation results over the entire dataset based on the error metrics for different models. These models include raw Wi-Fi PP counts, PFA, which we recently discussed, and variants of CountMeIn. We can see that the neural network model performs better than the regression model because of its ability to deal with extensive data. We can also see the effect of RSSI filtering on the lasso regression model in this table. To sum up the main findings of this paper presents CountMeIn, which is an adaptive machine learning system which calibrates Wi-Fi to precisely predict crowd numbers. It provides easy on-device edge processing and produces cutting-edge results for minutely and hourly crowd estimate. Based on the result of our pilot study's real-world smart city analysis, the advantages and disadvantages of our technology are evaluated. Thank you.